Before we start, I want you guys to know that your homework is going to actually be two sheets. The first is a 10 problem answer key attached on the front thing, separate paper, and the second is just a single, I'm going to kind of move away from there because I don't want you copying it, but it's a single kind of just simple version of this, but two worksheets. So we're going to start off with what these notes actually say, which is that by the law of exponential growth decay, how much things are changing by, in other words, the rate of change in a quantity, is directly proportional to how much is there. So if you think about it, the more you have, the more it's going to change the rate, or the less you have, the less it's going to change the rate. This is common in things like half-life. This is common in things like exponential growth of bacteria. If you let y represent how much is present at any time t, then the differential equation is written as this. This is something you should have memorized. The rate of change depends on how much is present. So K is referred to as the constant of proportionality. And if K is positive, then the amount that you have is increasing. Basically, step A here says that this is the law of exponential growth. If y increases as time increases, then our K is going to be greater than 0. And then exponential decay, that's the half-life thing, is if y decreases as your time increases, then K is less than 0. K is negative. So I guess I just wrote that there. K is the constant of proportionality. These are the different things that you can have it represent. Like I said, population growth and half-life, and then we also have compound interest. So anyway, one way to kind of build an equation is to actually to take the original dy dt equals ky and solve it subject to the initial condition that y of 0 is equal to this, what we're going to call y sub 0. That means I just have an ordered pair 0 comma y sub 0, which is just another way of saying we're going to plug in an initial y. So if I do what we did before and split this, dy is equal to ky dt, and then divide by y, I get dy over y is equal to k dt. That puts my y's on one side and the t's on the other. Integrate both sides and I get the natural log. The absolute value of y is equal to, and this would just be kt plus some constant c. Then if I plug this in, I get the, let's see, we plug in 0 for t, so that just gives me 0 plus c. Then I get the ln of y sub 0, and that's equal to c. So if I actually plug that back in here and kind of build another version of this, what I get is the ln of the absolute value of y is equal to kt plus the ln of the absolute value of y sub 0. And I can do e to the of both sides, exponentiate both sides with the base of e, meaning e raised to both of these. It's kind of a cheap way of writing that. So this just gives me absolute value of y, which is going to be positive anyway, so I'm just going to write y equals, we have e to the kt plus ln of the absolute value of y sub 0. And like before, that's the same as e to the kt times e to the ln of the absolute value of y sub 0. And this right here is just y sub 0. So this is good. Y is equal to y sub 0 e to the kt. And this formula here is that's the general formula for exponential growth or decay. It's also worth memorizing in its current form. Sorry, I'm pausing because I'm still on break and I'm trying to get my head back into the school mode. But anyway, example 1, if in a certain culture the rate of growth of bacteria is proportional to the amount present. That statement is underlined because that tells you that you're going to be using some version of dy dt is equal to ky. That's our exponential growth, that's our differential equation. That means that you can actually skip right ahead and use y is equal to y sub 0 e to the kt if you wanted to, because we know we've already done the legwork to build that. It says initially 1,000 are present and the amount doubles every 12 minutes. So amount doubles every 12 minutes, and if Y bacteria are present after T minutes, express Y as a function of time. So I know T is in minutes, and it's already been defined in terms of minutes, and Y is just straight numbers. So initially, my Y sub 0 is 1,000, and the amount doubles at 12 minutes. So what I can say is Y of 12 is equal to 2,000. That should be enough to kind of plug this in and basically solve for T. So I plug that in to 2,000 is equal to 1,000 e to the 12k. And if I solve, divide both sides by 1,000, 2 is equal to e to the 12k. And solve for k, I'm going to get k is equal to, take the ln of both sides, ln of 2 over 12. So what I can do is I can plug that back in and say this is now y is equal to y sub 0 e to the ln of 2 over 12 t. Now, it's worth noting how we're going to simplify this. So what I'm going to actually do is break this up into y sub 0 e to the, just make this the ln of 2 and then t over 12. And what that can be is the same thing as y equals y sub 0 e raised to the ln of 2 and then also raised this t over 12. That right there is equal to 2, so I get y sub 0. And I know y sub 0 was 1,000, so I'm going to go ahead and just put 1,000. E to the ln of 2 is the same as the number 2, t to the 12th. And that's my final. Actually, my final would be this, y equals. Then it says use a calculator. Hang on. Use a calculator to estimate how long it will take until 10,000 are present. So I can go 10,000 equals 1,000 times 2 to the t over 12. Divide by 1,000, and I get 10 is equal to 2 t to the 12, or 2 to the t over 12. If I want to solve this equation, I can take the natural log of both sides. Ln of 10 is equal to t of, let's see, ln of 2 to the t over 12. Let me write that better. And that t over 12 can come out in front, and so I get ln of 10 is equal to t over 12 times the ln of 2. Then if I multiply both sides, or actually we'll just go ahead and solve for t, I get t is equal to 12 times the ln of 10 over the ln of 2. And that's an exact. My approximate would be t would be about, if I plug it in, I'm going to get 39.86 minutes. I kind of just skipped. All this should actually probably be down here. Using a calculator to estimate, I can do it by graphing. So if I go to the graphs and just enter, would be 1,000 times 2 raised to the x over 12. And then set the window to be something where t could be a little bit bigger. Like maybe t could be 50. And this would have to go way up to maybe like 12,000. Then I can see, alright, so here's a graph of it, and it wants to know how long until 10,000 are present. Well, I can just graph y is equal to 10,000. And do a quick intersection. And see it's about 39.9. So that confirms what we had before. Just trying to point out that you can do it. I'll just draw and sketch a graph. Just say we found the same thing. Okay, next. In the course of a year, the number of cases of a disease is reduced by 20%. If there are 10,000 cases today, how many years will it take to reduce to 1,000? Then it says assume the law of exponential growth applies. That is also underlined here to show you that we can use this y equals y sub 0 e to the kt. So let's see. It says the number of cases each year is reduced by 20%. So that means that I have the ordered pair 1, well, I know that 0, comma 10,000 is an ordered pair, but then I know 1, comma reduced by 20% means that there would be 8,000 left. So I can plug that in and say that 8,000 is equal to 10,000 e to the k times 1, so that would just be e to the k. Then I have e to the k is equal to 4/5, or k is equal to the natural log of 4/5. Plugging that back in, I get y equals, let's keep the 10,000, e to the ln of 4/5 t. And for reasons before, that's going to be the same as y equals 10,000 times 4/5 raised to the t. So that becomes our formula. Then it says how many years will it take to reduce the number to 1,000. Well, I'll go ahead and just put 1,000 in for y. Oops, not that's times. Then I get 1/10 equals 4/5 to the t power. If I get t by itself, take the natural log of both sides, I get t equals the ln of 1/10 over the ln of 4/5. You don't need to simplify it any more than that. Just get it in a calculator ready form, plug it in, and you're going to get about 10.32 years. Okay, last one, the rate of decay of radium. I see rate of decay, that's kind of lets us know we're doing exponential growth decay. Is proportional to the amount present at any time t. Okay, that whole thing now is really screaming at you. This is exponential growth and decay. Y is equal to y sub 0 e to the kt. The half-life of radium is 1690 years, and there are currently 20 milligrams present. So I know that y of 0, actually I'll just write them as ordered pairs, 0, comma 20, and then it says the half-life is 1690 years, so in 1690 years, that there's going to be half of that left. That's going to be 10. It's also worth noting that time t, we're going to want to define t is in years. That should most likely, I mean, in a good problem that's stated, yeah, it's stated right here. T is, it should be defined in the problem as being in years. So let's use this information. 10 is equal to 20 e to the 1690t, and I get 1/2 equals e to the 1960t, or k, sorry. This should have been a k right here. And I get k is equal to the ln of 1/2 over 1690. Putting that back in, I get y is equal to 20 times e to the ln of 1/2. Then I have that times t over 1690. That's just substituting this in for k and doing a little manipulation. So this part here can become 1/2 raised. So I got 20 is equal to, or y is equal to 20 times 1/2 to the t over 1690. And you might also see that as 20 times 2 raised to the negative t, 1690. Those are the same thing, and you should see why those are the same thing. It says how many years will it take until there are just 3 milligrams of radium left. Well, if I plug that in, 20 times 2 to the, let's see, oh, no, sorry, not substituting 3 in for t, I'm saying 3 equals 20 times 2 to the negative t over 1690. So I have 3/20 is equal to 2 to the negative t over 1690. Take the natural log of both sides, and I get ln of 3/20 over, this would be the negative ln of 2, or the ln of 1/2, and then times 1690. It's going to equal t. So t is equal to 4625.47 years.